Robots in space.
Hello everyone, I'm Mike DiVerde and I'm an aerospace engineer. Today I'm wearing my Delta rocket shirt. On the left you see a Delta IV heavy liftoff, and on the right the black cone is the type of payload adapter that I designed for 4-meter and 5-meter rockets 30 years ago. The silver cylinder is the mass and stiffness simulator that flew on the very first Delta IV heavy flight. But hanging off the side of the silver simulator is a very interesting payload. I worked with the Air Force Research Lab to develop, fab, assemble, and fly in 30 days a support for their nanosat launch. On today's episode of Robots in Space, I will discuss research by Chinese scientists on a large solar energetic particle event and the impact of Mars measured by the Chinese Tianwen-1 Mars orbiter, along with data from 3 other spacecraft. The radiation environment at Mars is very harsh, and it is not well understood, which makes this research important. Tianwen-1 was China's first successful Mars mission, launched on July 23, 2020. The mission consisted of an orbiter, lander, and rover named Zhurong, making China the second nation after the United States to successfully land and operate a rover on Mars. The mission represented a significant achievement for Chinese space program and contributed valuable data about Mars geology, climate, and potential water ice deposits beneath the surface. The spacecraft reached Mars orbit in February 2021, and on May 14, 2021, the lander successfully touched down in Utopia Planitia, a large plain in Mars' northern hemisphere. The Zhurong rover, equipped with cameras, ground-penetrating radar, and instruments to analyze Mars climate and geology, operated on the surface for about 1 Earth year, far exceeding its planned 90-day mission. The rover entered dormancy in May 2022 due to declining temperatures and dust storms. And while attempts were made to reestablish contact, it has not responded since. The orbiter continues to function, conducting its own scientific observations of Mars and serving as a communications relay. The Mars Energetic Particle Analyzer, MEPA, was one of the scientific instruments aboard China's Tianwen-1 orbiter. It was designed to study energetic particles in Mars' space environment, particularly focusing on measuring solar energetic particles, SEPs, galactic cosmic rays, GCR, particles trapped in Mars' weak magnetic field, the interaction between solar wind and the Martian atmosphere. MEPA had the capability to detect ions with energies between about 50 kiloelectron volts to 12 megaelectron volts, and electrons from 50 kiloelectron volts to 6 megaelectron volts. The instrument helped contribute to our understanding of Mars' space weather environment and the planet's interaction with solar radiation. Let me break down the key differences between some of the solar phenomena. Solar energetic particles, SEPs, are much higher energy particles compared to the solar wind. They can be accelerated by both solar flares and coronal mass ejections. Energies range from a few mega electron volts to giga electron volt levels. They can pose significant radiation hazards to spacecraft and astronauts. They occur intermittently, usually associated with solar events. Now, solar flares are sudden, intense bursts of radiation across the electromagnetic spectrum. So, not particles, but radiation, photons of different frequencies. They primarily emit X-rays and extreme ultraviolet radiation. They can accelerate particles to create SEPs. They travel at the speed of light and reach Earth in about 8 minutes. They generally last minutes to hours, but they can disrupt radio communications on Earth's day side. Now, the solar wind is a constant stream of low energy charged particles, mostly protons and electrons, flowing from the sun. Typical speeds range from about 300 to 800 kilometers per second. They're always present, creating this continuous background flow in space. Shapes the heliosphere and interacts with planetary magnetic fields. Now, on the other hand, magnetic storms are large-scale disturbances in Earth's magnetic field. They're usually caused by coronal mass ejections hitting Earth's magnetosphere. They can last for days, and this is where you've seen your aurora. This is what the magnetic storms are, what's behind your visible aurora at high latitudes. They can induce currents in power grids and pipelines. They affect satellite operations and navigation systems. They're not a direct solar phenomenon, but rather Earth's magnetic field response to solar activity. A key distinction to remember is that solar wind and magnetic storms are broader environmental phenomena, while solar flares and SEPs are more discrete events. They're all interconnected, though. For example, a solar flare might produce SEPs, which then interact with the solar wind and potentially trigger a magnetic storm at Earth. An astronaut traveling to Mars might encounter solar energetic particles, SEPs. They're produced by solar flares and coronal mass ejections. They're primarily consisting of protons and electrons. They're more intense but sporadic exposures, and they can deliver very high radiation doses during solar events. Here are the effects at different dose levels for acute exposures. So, in the range of 50 to 100 milligray, and milligray is your unit of radiation, right? Between 50 and 100 milligray, there's mild blood count changes that might be detectable. There's no immediate noticeable symptoms. There's slight increases in long-term cancer risks. But then you get to a zone of 500 to 1,000 milligray. Now you have the definition of this whole body exposure threshold for radiation sickness at 500 milligray. So that's the level that we're going to be very concerned about, right? Nausea and fatigue may occur. There's temporary changes in blood cell counts. There's much more significant risk, increase in cancer risk. And there's usually no immediate severe effects. Now let's put these levels in perspective for a moment. For context, when you get a typical chest x-ray, you're getting about 1/10 of a milligray. Now, 1 milligray is actually defined by this. It's the average accumulated background radiation dose to an individual over a 1 year period as somebody who lives in the United States. So your typical American getting an average amount of radiation during a full year is going to get 1 milligram. Now, on the other hand, the astronauts on the International Space Station might receive between 50 and 100 milligray per year. So you see that they're getting like 100 times more radiation exposure in space. One thing to keep in mind as we go on to Mars is that even the astronauts on the space station have protection from Earth's magnetosphere, and Mars, they will not. Now we will discuss the primary research paper entitled the 2022 February 15 Solar Energetic Particle Event at Mars, a synergistic study combining multiple radiation detectors on the surface and in orbit of Mars with models. The research paper concludes that the February 15, 2022 Solar Energetic Particle Event at Mars was significant in enhancing our understanding of Mars' radiation environment. The study combined data from multiple spacecraft to reconstruct the SEP energy spectrum and assess the radiation doses at Mars orbit and surface. They had data from multiple spacecraft, including the Chinese Tianwen-1, which provided high-energy proton flux measurements between 20 and 100 megaelectron volts, using the Mars Energetic Particle Analyzer, MEPA. The American MAVEN orbiter offered continuous low-energy SEP measurements below about 6 megaelectron volts. The European ExoMars Trace Gas Orbiter conducted orbital radiation dosimetry measurements using the Leolin MO dosimeter. The American Curiosity rover, one of my favorites, measured surface radiation using the Radiation Assessment Detector RAD. The second type of evidence for their conclusions includes the reconstruction of the SEP energy spectrum. The study reconstructed the SEP energy spectrum from 1 megaelectron volt to 1 gigaelectron volt by combining data from MAVEN, Tianwen-1, and Curiosity. The reconstructed spectrum was validated against dosimetry data from Trace Gas Orbiter and Curiosity. The third type of evidence for their conclusions is their radiation dose calculations. The calculated radiation doses at Mars orbit and surface were compared to the recorded doses, showing a discrepancy of less than 25%, which validates the reliability of the reconstructed spectra and measurements. The study emphasizes the necessity of continuous and synergistic radiation monitoring at Mars to better understand and mitigate the radiation hazards for future crewed missions. Overall, the study highlights the critical role of combining data from different spacecraft to provide a comprehensive assessment of the radiation environment at Mars, especially during large SEP events. Quoting from the paper now, there is a growing interest in exploring Mars in the coming decades. However, a significant obstacle that remains is the presence of space radiation, which poses a considerable and unavoidable threat to crew health, especially during long-term stays in future Martian habitats. Of particular concern are sporadic energetic particle events caused by strong solar eruptions, which can increase radiation levels in deep space and near Mars to potentially dangerous levels. Notably, a solar energetic particle event on 15 February 2022 has caused the first significant radiation enhancement at Mars in solar cycle 25, as observed by ESA's Trace Gas Orbiter, the Chinese Tianwen-1 orbiter, as well as NASA's Mars Atmosphere and Volatile Evolution spacecraft, and of course, the Curiosity rover. By combining data from measurement and modeling techniques, we reconstruct the energy spectrum of this SEP event to understand the potential radiation hazards at Mars. My summary is that the research paper did a good job in combining data from several spacecraft to assemble an overview of the radiation environment at Mars during one solar energetic particle event. The data highlights the radically different and harsh environment at Mars that humans, livestock, and plants would encounter on Mars compared to the very benign environment that we all enjoy here on Earth. On Earth, we are shielded by a huge and powerful magnetosphere, and we are safe. On Mars, there is no magnetosphere, and it is dangerous. Of note are the gaps in data that the paper points out, even when using what is available from multiple spacecraft. The entire spectrum of radiation is not covered. Some instruments are pointed away from the sun and some towards the sun, and then some will vary in vector direction during the event. Each instrument has variable degree of shielding, either from the planet or the atmosphere or the spacecraft itself. Some instruments were overloaded by the intensity of the event, and valuable data was simply lost. The point is that there is not nearly enough instrumentation to determine what the radiation environment is at Mars. And that suite of instruments will need to collect data for a very long time first, because these powerful radiation events occur sporadically and unpredictably. Only with this long baseline of quality data can the hazards be clearly understood. Without that deep understanding of this deadly environment, then it is not possible to provide a safe habitat on Mars for plants, livestock, or humans when they live there. Someday. Omni futurists